Welcome back everyone to 11.1 sequences. In this video I have a few more definitions to go over with you along with a few examples. However, I'd like to start off with going back to this theorem 11.1.5 and giving you a little bit more of an intuition about what sequences kind of look like, a way we can visualize them, and then really giving you an appreciation for what this theorem is telling us, because this is a very powerful theorem that'll help us calculate out a lot of limits. So let's get to it. So the first thing I want to do actually is take a second to draw out a picture of what this is telling us here. So I'll go ahead and erase a little bit, and this will be my spot here for a picture. Okay, so I want to show you how the function f of x and the sequence a sub n are related. So let me go ahead, yes, I'll draw some axes here. And let's suppose that we have a limit L. So this is going to be my L, and this would be the limit that my function approaches. So there's my nice function here. This is my f, and it approaches L as x gets very, very large. Now let's go ahead and mark off some integers, 1, 2, 3, 4, 5, so on and so forth. And the claim is that my sequence is actually equal to the function's value at these integers. So at 1, this is my A1, here's my A2, A3, A4, A5, so on and so forth. So these are my sequence terms, like I mentioned, A1, A2, A3, so on and so forth. So this is why, as my function approaches L, because how my an are defined, right, they will also approach that same L as we get larger and larger and larger. So that's what this theorem is telling us here. Really, this restriction making our function equal to this a sub n, this is what gives us all the power. Okay, now let's go back and do a quick definition. We have a sequence is called increasing. If, well, it increases, and usually this is defined as a sub n is less than a sub n plus 1, so the next term is bigger than the previous term, for all n greater than or equal to 1, so that's a1 is greater than a2 is greater than a3, so on and so forth. We can say it's called decreasing if, well, kind of the opposite holds. So if a sub n is greater than a sub n plus 1, for all n greater than or equal to 1, a sequence is called monotonic if it is either increasing or decreasing. So it's monotone. It heads in the same direction. It's either always increasing or always decreasing. And then finally, if our function is increasing and our function f of n is equal to a sub n, then our sequence is also an increasing sequence. And similar for decreasing. So I'm going to show then that this sequence, 1 over 2 to the n power, is decreasing, and I'm going to show this in a couple of different ways. So I'm going to first just show that using our definition for what a decreasing sequence is, that this is indeed decreasing. So let's then compare 1 over 2 to the n with 1 over 2 to the n plus 1. And the claim is that if this is a decreasing sequence, well, then the first one should be bigger, right? So I'd like to prove this, and I'm going to kind of work in this backwards order to try to get to this. So, well, one thing that I could do, let's go ahead and rewrite this one more time. So this 1 over 2 to the n compared to this 1 over 2 to the n plus 1. Well, this 1 over 2 to the n plus 1 is really 2 times 2 to the n, right? So now you can notice that, well, I have a 1 over 2 to the n in both of these cases. On the right-hand side, I have a 1/2, and on the left-hand side, I have really, there's a secret 1 here, right? 1 times 1 over 2 to the n. So then, well, the claim is that we're actually done, right? Since 1 is greater than 1/2, then we can multiply both sides by 1 over 2 to the n, and we would get the result that we wanted, right? That this is a decreasing sequence. And the big thing here is that, well, 1 over 2 to the n is positive, so you never have to worry about this inequality flipping. So this is one way that we could show that we have a decreasing sequence. But sometimes these sequences are very complicated and we couldn't pull off a trick like this. So then it's useful to remember, well, I know how to show a function is decreasing. So instead of looking at 1 over 2 to the n, I can look at the function 1 over 2 to the x, let's say. Or this is the same thing as 2 to the negative x. And I could show that this is decreasing. Well, what does it take for a function to be decreasing? Well, usually we say that its derivative is negative. So let's take its derivative really quick. We take the derivative of 2 to the negative x. So we get natural log of 2 times 2 to the negative x times negative 1, thanks to the chain rule. And now let me go ahead and rewrite this. So this is negative natural log of 2 times 2 to the negative x. And the claim is, well, at this point, we can say that this thing is always negative, right? Because 2 to the negative x is always positive, always greater than 0. And negative natural log of 2, well, this is just a negative number, right? So if you take a negative and you multiply it by a positive, you get negative. So for any x, the derivative is less than 0. So therefore, f of x is a decreasing function. Then we can apply the theorem that says, well, our function's decreasing. So then by this theorem, 11.1.13, we know that our sequence is actually decreasing. Our sequence here, right, is this 1 over 2 to the n. So this is a decreasing sequence. So this is an example of how you could apply the theorem to show that our sequence is decreasing. Okay, let's do a little bit more practice. We'll see in our homework, our web work, that there are quite a few of these where it wants you to find a formula for a sub n. So let's get a little bit more practice of, if I give you a list, a sequence, can you figure out this nth term? So we have 1, negative 1/2, 1/3, negative 1/4, and I'd like to find a formula for an, this nth term. Well, okay. One thing we could say, instead of 1, I could write this as 1 over 1. Because now this kind of, we see maybe a pattern. So remember, the first number here is our a sub 1. So if I plugged in 1, second number is a sub 2, third number is a sub 3, then a sub 4. And right, you can see these 1, 2, 3, 4s exactly match up with the denominator. So we could think maybe our sequence is something like 1 over n, right? But this gives us 1, 1/2, 1/3, 1/4. So it gives us kind of the right values, but not the negative positive, right? We should have a couple negatives here whenever we have evens. Negative 1/2, negative 1/4. So how do I get those negatives? Well, there's a couple ways that we could go about doing this. The first is that we could technically use a piecewise defined sequence, or a piecewise defined function here. And we could say that a sub n is equal to, well, 1 over n if we have an odd denominator. So if n is odd. And we could say negative 1 over n if n is even. And this is technically correct, but you'll find when you're doing your homework that there's not a good way to plug this in into the system. So there's actually a trick here to go back and forth between negative and positive and negative and positive. You can actually use something else, and you can write it a lot nicer than this. You don't have to use the piecewise defined stuff. So the nice way to do this is actually with using this idea of negative 1 raised to the n power, right? Because if you go ahead and you take this and you plug in 1 for n, negative 1 to the first power will be negative 1, negative 1 to the second power will be 1, negative 1 to the third power will be negative 1, negative 1 to the fourth power will be 1, and so on and so forth. Now this is very close to what we want, right? We could say an is this 1 over n times negative 1 to the n, but then we would have negative 1 here, and we'd have a negative 1/3. So this wouldn't exactly, it doesn't exactly work out. We would have the wrong terms are negative. So one thing we can do in order to shift this a little bit is we can consider, instead of -1 to the n power, we could do -1 to the n minus 1 power. So now let's go ahead and check, right? If I was to plug in 1, well, 1 minus 1 would be 0. -1 to the 0 power, well, anything to the 0 power is 1. So that's positive. Great. How about -1 to the second power? Well, 2 minus 1, so that's -1 to the first power. That's going to be -1. So this is going to be -1/2. Perfect. And now if I plugged in 3, well, 3 minus 1 is 2. If I take -1 and I raise it to the second power, well, that's going to be +1, so this works out. And then 4 minus 1 is 3, so -1 to the third power, that's going to be negative. So this is indeed giving us exactly what we wanted. So remember, whenever you need to kind of alternate back and forth between negative and positive, using a -1 to a power is a really good way to go. Okay, let's do a couple more examples here. I have the sequence 1 plus 5n divided by 3 minus 2n, and I'd like to find the limit of the sequence. So as n gets very, very large, what does this head towards? Well, let's go ahead and write out maybe the first few terms just to, again, kind of get an idea here. If I plugged in 1 for n, I'd get 6 over 1. If I plugged in 2, I'd get 11 over -1. If I plugged in 3, I would get 16 over, let's see, that'd be -6. So 3 minus 6 would be -3. And it would keep on going forever. Okay, so my claim is, instead of looking at the sequence, let's look at kind of this equivalent function here. So the function that takes on these values, integer values, is going to be f of x is equal to, and just everywhere I see an n, I'm going to replace an x. So this is a function, and I can try to figure out what is the limit of this function. Well, we should remember back in the days of Calc 1 how to figure out horizontal asymptotes, right? This was the idea as x gets very, very large. And the idea was to divide through by this largest power of x. So if I divide through by 1 over x, well, I get 1 over x plus 5 divided by 3 over x minus 2. And as x gets very, very large in this case, well, this 1 over x and 3 over x are going to 0. So I get 5 over -2. So the function approaches 5 over -2. So therefore, my sequence also approaches 5 over -2 because of the theorem that I had from up above, 11.1.5. Okay, so then let's move on to another problem. So it looks like my sequence in this case is really kind of an addition of two sequences, right? There's this -1/5 to the n, and then there's sine of n over n. So we're really going to be using this theorem, this 11.1.7, that says, well, let's just try to figure out the limit of each of these individual pieces. And then if I can figure out the limit of the individual pieces, I can add those limits together. So how about this -1/5 to the n power? What is that going to approach as n gets very, very large? Well, the claim is we should actually know this. And this is a theorem that we had from before. Here it is. -1/5 is between -1 and 1. So therefore, as n gets larger and larger and larger, this is going to be approaching 0. So this first term right here will approach 0 by, our theorem here I believe was 11.1.11. And how about this second term here? Just rearrange this. So the second part, sine of n over n, well, this should remind us again of the squeeze theorem idea, right? Sine is bounded between -1 and 1, and I could divide through by n on all sides. Remember, n is a nice positive integer, so you don't have to worry about flipping those inequalities. So then -1 over n goes to 0 as n approaches infinity, and 1 over n approaches 0 as n approaches infinity. So therefore, by the squeeze theorem, we know that the middle term, right, the sine of n over n, must also approach 0 as n approaches infinity. So this is kind of a sad sequence to some extent, right? So you have 0 plus 0, and that's just, well, 0. Okay, I have one more for us. A sequence natural log of 3n over 2n, find the limit. And so looking at this, I really want to consider its function, f of x, which is the natural log of 3x over 2x. So again, I'm just placing n's with x's. And now I can think about how can I figure out the limit as x goes to infinity? Well, the natural log of 3x would go to infinity and 2x would go to infinity. So this is an indeterminate of form infinity over infinity, which means I can use L'Hopital's rule. So L'Hopital's rule for functions says that, well, instead of looking at this limit, I could take the derivative of the numerator and derivative of the denominator and look at those limits. So let's see, 1 over 3x times 3 and 2, a little bit of cancellation here. And as x gets very, very large, this is going to be heading towards 0. So therefore, we know that our sequence must also approach 0. So this is very nice, being able to switch to a function and then apply L'Hopital's rule. This is a very nice trick. All right, and that should just about do us here in 11.1 sequences. As you can see, we have a lot of structure set up for limits of functions, right? We know about horizontal asymptotes, we know about L'Hopital's rule. So when in doubt, you have a nice sequence, you can go ahead and look at its corresponding function. All right, I'll see you next time in 11.2.